Welcome to Quantum Curious, where we explore the fascinating world of quantum science. I'm Mohammad Yas, and I'm thrilled to have you here for our very first lecture on quantum optics. I'm a postgraduate researcher and working on quantum cryptography. I've created this channel to share my passion for quantum science with learners like you. So, this is our first lecture on quantum optics, and The this series of lectures will follow the two books, that is Quantum Optics for Beginners and Introductory Quantum Optics by C.C. Gary and Peter Knight. And for some special topics, we will also follow the book by Marlon Scully and Suhail Zuberi, and this is the standard text that is mostly used in many universities. So this lecture will comprise of introduction and motivation behind quantum optics, and we will discuss some elements of uh, electromagnetic theory, and this description will go on to 2 or 3 more lectures to get some tools and some insights about the classical theory, and this will be helpful in the later lectures when we will delve in more deep into the quantum optics. So the quantum optics is just the study of interaction between matter and radiation fields and the domain where quantum effects are important. So it is interested because we can get some conceptual insights and intuition uh, on the foundation of quantum mechanics, and because we are working with very uh, with the very small microscopic particles like photons and its interaction with atoms, so we can get more intuition on the foundations of quantum mechanics. So the first question is that why we need radiation field to be quantized. So for many phenomena like diffraction and interference, uh, the electromagnetic wave nature works very well. So there are two domains in which we treat the classical light, or you can say electromagnetic wave, in two different as two different uh, perspective from the two different perspective that it depends upon the approximation we need. So for most of the phenomena, the semi-classical theory works very well, in which we treat radiation sources as quantized, but the electromagnetic waves are just the same classical wave. But for phenomena like anti-bunching and squeezing photons, we usually use the quantized version of electric field, and electric field and electromagnetic wave in general. So we will see how these two domains works in the upcoming lectures. So first 2 or 3 lectures will comprise of just the review of classical theory of radiation field, and we will treat the radiation field as non-interacting harmonic oscillators, and we'll apply the standard quantization formalism on these harmonic oscillator to get some insights about the energy and amplitude of the electric and magnetic field and electromagnetic waves in general. So let's move on to the general description of electromagnetic theory. We know that Maxwell's equations are just the cornerstone of classical electromagnetic theory. So there are 4 Maxwell's equations that define the electromagnetic wave and its properties. So the first two are just the Gauss's law in differential form. So the first equation states that the flux of electric field can be calculated just by passing through the surface by just the enclosed charge in that volume. And the second equation states that the magnetic field uh, does not have the properties such that like the electric field, as it has no net flux passing through the surface. because we do not have any kind of magnetic monopoles in nature. The third equation is just a differential form of Faraday's law, and it states that the varying magnetic field induces the electric field. And the third equation is the Ampere's law with Maxwell correction, and it states that the magnetic field is can be produced by the charge density and varying magnetic electric field. So electric and magnetic field are can be described by these four equations, these four coupled equations, and in with the solution from the solution of these equations we can calculate the magnetic field and electric field at certain point where we have charge and charge density and current density. So from another interesting thing we come to know from the solution of these Maxwell equations that light is just an electromagnetic wave, and the properties of vacuum like permittivity of electric field and magnetic permeability are related with speed of light c by this relation. So we cannot directly integrate the Maxwell's equation and get the field required. So we can introduce an ingenious mm, procedure by introducing the concept of scalar and vector potential, and we could derive the vector and scalar potential from these Maxwell equations, and from these scalar and vector potential we can retrieve the magnetic fields that are physical observables mainly. So the first concept and the first aim is to uh, write the magnetic and electric field in the form of vector potentials and scalar potentials. So from equation 2, that is Gauss's law for magnetic field, we uh, mm, can see that its divergence is zero. So from vector calculus, that any magnetic field that has divergence zero, we can uh, write the vector field in the form of the curl of a vector potential. And from uh, uh, electrostatics, we know that the electric field is just a negative of the gradient of the scalar potential. And also from V equation 3, we can infer that the electric field is just a change in is equal to a change in vector potential, time derivative of vector potential. So combining these equations, we can write the electric field in terms of scalar and vector potential. So we want to know that how these vector and scalar potentials are related, and uh, uh, how they how the condition is imposed by the uh, electric and magnetic field when they follow the Maxwell equations on the vector and scalar potential. So when we put the form of the electric field in terms of scalar and vector potential in equation 1, we get this condition that is followed by the vector and scalar potential when the electric and magnetic field follow the Maxwell equations. So we have the required form of magnetic and electric field in form of vector and scalar potential. We can put these form in the equation 4. Equation 4. So we get this scary equation, you can say. So our aim is to get the differential equation from which we can uh, get the solutions to calculate the field required. So the left-hand side could be calculated by using an identity from vector calculus, and in result the equation becomes this. And rearranging this equation in the form of this equation is very helpful, as we can see that the left-hand side is just like a wave equation, and this is an inhomogeneous part of the differential equation. So our aim is to get the simplified differential equation so we can get the vector potential, and from that potential we can retrieve the magnetic fields required, or magnetic fields or electric field required. So, but there is a problem that magnetic field is just in the form of the curl of a vector potential. But from the Helmholtz theorem, we required the curl as well as the gradient of the vector potential, the gradient of the scalar potential. So to fulfill that requirement, we have to modify our definition of vector potential and scalar potential. We use the concept of gauge transformation that fulfills that task, and we know that the magnetic and electric field are gauge invariants as the transformation of the transformation of vector potential and scalar potential does not affect the physical observables that are more interesting uh, from this formalism. So the condition is also fulfilled under gauge transformation, and we could further simplify our equation 11 by using the concept of the Coulomb gauge. And this states that the vector potential has no longitudinal component, and as we know that we have a freedom to choose the vector potential, we can also make the choice of scalar potential. So using these assumptions, we could greatly simplify our equation 11, and we could see that it becomes in that form. And this is precisely the form we were aiming to, and this is called the wave equation. And it could be solved by using the techniques like separable of variables or Fourier and then transform and Fourier analysis. So the solution of the wave equation is in that format could be verified by putting that form in this equation. So here subscript ks is the amplitude of the wave, and omega ks is the angular frequency of the wave, and k is the wave vector that is describing the propagating direction of the wave. So from the Coulomb gauge, we can infer that the propagation direction of the wave and amplitude of the wave are orthogonal to each other. So they are orthogonal, so we can decompose the amplitude into two transverse components that have uh, unit vectors like ek1 and ek2, and as they are proportional, as they are transverse to wave direction, so they have cross product is equal to k and k vector. So to get the real vector potential, we have to add the imaginary and real part of the solution of the wave equation, as because the wave equation has infinite solution, because we have imposed no constraint on the wave, so it can have any kind of amplitude and angular frequency, and it can have any kind of energy. So by using these unit vectors, we could write the resulting wave vector in that form. You can say vector potential in that form. So from this vector potential, we can directly calculate the electric and magnetic field as desired. So our aim is fulfilled, and we have successfully solved the problem in our hand. We had in our hand. So the visualization of electric and magnetic field is quite simple and quite beautiful, as we can see that the amplitudes of electric and magnetic field are mutually orthogonal and also orthogonal to the propagation direction of the wave. So uh, this is the plane wave solution. This is the consequence of the plane wave solution of the um, uh, wave equation, and the in vacuum Electric and magnetic field are plane waves, and they fulfill the condition that we described earlier. So that's all for today's introduction to quantum optics. I hope this gave you a solid starting point for more in-depth lecture on quantum optics. Until next time, let's keep decoding the quantum world together. Thank you.